Oh, good afternoon. This is Mr. Precella, and we're looking at systems of equations and matrices and Cramer's rule today.
It might not mean anything to them at this
Well,
point.
it will by the end of class. So let's switch over to my paper. I need to talk a little bit first. Let's lower this thing down, and let's move this timer over to the left side. Okay, systems of equations. We'll start off, as I said, there are three distinct topics that are all connected. Systems of equations, matrices, and Cramer's rule. We'll start with...
Why don't we first show them what a system of equations is?
Oh,
What do you think? Okay. System of equations, we just mean two or more equations. Like right here, solve the following system of equations. This is two equations. You want to know one answer for x and one answer for y. That'll make both of them true.
Look at those equations. Look at that first equation, 7x plus 3y equals a negative 41. If you were to draw a graph of that, what would you expect it to be? I don't see any exponents. I don't see any square roots. Just a slanted line. Okay, so we have two lines. So what we're doing is we're trying to find the solution to that system, which means we're trying to find the point of intersection or points of intersection. There could be more than one. Let's switch to the paper here, okay? I want to look at there are three possibilities when looking at systems of linear equations. The most common, you have two lines and they intersect in a single point. That's what usually happens, okay? There's one unique solution. There's one point of intersection.
Here's a thought question. Could you have two lines intersecting in exactly 3 points? Could you draw two lines and they intersect in exactly 3 points? Well,
no, that couldn't happen. So you can have one unique point of intersection. The other possibility is they don't intersect at all.
What do you call two lines that never intersect? Starts with a P.
Parallel lines. Okay, they're parallel. So, no point of intersection. There's one other case, sort of a case that people generally don't think about. It's called coincidental lines. You have one line, and then you have another line sitting. Oh, let's see. There are three possibilities. There's the first possibility. There's the second possibility. Here's the third possibility. You have one line, and then you have the second line sitting right on top of it. These are called coincidental lines. How many points of intersection would they have? They're coincidental lines. One line is sitting on top of the other line.
Is it every point?
Every point is a common point. There's one line sitting on top of another. So there's infinitely many points of intersection.
So with two lines, you either have one point of intersection, no points of intersection, or infinitely many. So going back to my question, could you draw two lines that had 3 points of intersection?
Exactly 3? No. Could you draw two lines that have exactly 2 points of intersection? No. No. Exactly 2? The only possibility is 1 point, no points, or every point. So we're going to look at two different methods of solving systems of equations. And to solve a system means to find the point or points of intersection. So let's see, to solve a system of linear equations, we will use substitution or elimination. By the end of the class, you're going to know a new method, an advanced method that uses matrices and determinants. But the two basic methods of solving linear systems, or any system of equations, even if it's not linear, substitution and elimination. So let's look back at that number 1.
And look at this. The way the answers are written here, the solution is you type an ordered pair. That'll be what you use if there's just one point of intersection.
And that's the most common situation.
Now for the other two unusual ones,
infinitely many solutions. What would that be? Look at my little picture here. I'll kind of switch over. Which one would have infinitely many solutions?
well, the
The coincidental lines. And the other option, there's no solution. Which one would have no solution? The parallel lines. They never intersect. Okay, so here goes. To illustrate elimination.
No, substitution.
Substitution. I prefer elimination, but this problem is tailor-made for substitution. Let me write the two equations down. We have 7x plus 3y equals a negative 41. And then x is equal to 12 minus 4x.
4y.
Oh, yeah.
Hey, can you make that an 8y? No, of course not.
Why would I make it an 8?
So 12 minus 4.
Oh, okay. Oh, I see. You were asking the questions.
Yes.
I mean, the students a question.
Yes.
Okay. Switch over to my paper.
And this is called the substitution method, so we're going to do some substitution.
With substitution, you need one equation solved for a single variable. And fortunately, this one's already solved for x. So what we're going to do, we're going to take the 12 minus 4y, and we're going to substitute it for x into that green equation. So instead of 7x, just like the name says, substitution, we're going to go 7, replace the x with 12 minus 4y. We still have that plus 3y equals a negative 41.
So we've gone from two equations with two variables.
Look at this. Now we have one equation with just the same variable, y. We know what we're going to have to do here. We're going to have to get y by itself, and whatever the number is on the other side, that'll be the solution for y. So let's get rid of the parentheses by distributing there and there. 7 times 12 is 84 minus 7 times that minus 4y is going to give me, okay. And we still have the plus 3y equals a negative 41. We have like terms here with y's. Negative 28 plus 3, that's a minus 25y equals a negative 41. There's really only one sensible next step. We're trying to get y by itself. What do you think I'm going to do? Minus the 84, I agree. Minus the 84. I don't know why I'm showing this. I quit showing that step a long time ago, didn't I?
Yeah, but again, you could have been doing this on day one.
Negative 41 minus 84. Is that a negative 125? Only one step left to get y by itself. What do I do?
Divide 25.
Okay. Negative 125 divided by negative 25, negative divided by negative is a positive 5, I agree. So what you know now, you know that these lines are going to intersect in one distinct point of intersection, and that the y value is 5. So here's what your solution is going to look like. The y value is 5. How will we find the x value for this ordered pair? Remember, the name of this method is substitution. Okay, you already have one equation solved for that x variable. So substitute that 5 into that equation that was solved for x. So
Theoretically, you could use the other one.
you could use the other one, but it's just more work. This one already has x by itself. So we're substituting a y value of 5. So we have 12 minus 4 times 5. That's 12 minus 20. So we have an x value of negative 8. So we now know for these two lines, if we were to graph those two lines, they would intersect at the ordered pair negative 8, comma 5. Any questions there?
Right here, why don't you draw a little ordered pair, x, y?
Oh, I like that. Okay. That means there'll be one point of intersection, and that's what we just found. We found that one point of intersection, negative 8, comma 5. Any questions there?
So we got to make sure we enclose them in parentheses. Okay.
If they say to type your answer as an ordered pair and you just write negative 8, 5, well, here they'd let you correct it. But on the test, do you get to correct it like that? You would count it wrong. Make sure you study those instructions. How do they want your answers?
Student
Any
was
questions?
so smart that time when he told me 30-something years ago that this damn teacher tells him to study the instructions. Little
Okay,
did he
next
know
question.
we'd still be talking about him all these years.
Perhaps some might say you would still be ridiculing
No,
him,
I'm just
okay.
no, but that was a good thing. It changed how I taught, and I started telling the students, study the instructions. Okay?
The same instructions here say solve using substitution. 4x plus y equals 22, and 7x minus 2y is equal to 16.
Did the first one say solve by substitution?
Yes.
Yes.
I think it'll always give you a method, but when you're actually taking the test,
If it said substitute, like go to number 1 is tailor-made for substitution because one of the equations is already solved for one variable. You see, it's already there, that x equals. But look at number 2. I don't think it's tailor-made for substitution because you don't have one of the equation variable equals. But you're going to have to modify it. If I were doing this just for my own sake, I'd use elimination. We'll see that in a moment. But they'll give you a method, the method that they think is best for the problem, okay? If they say solve by substitution, then they think that there's a variable that's pretty easy to get by itself. Looking at this, there's one letter, switch over. There's one letter that you could get by itself real easily.
by that we mean without dividing and getting
fractions. Which letter would be the easiest to isolate? The y in which equation? Equation 1 or equation 2? Equation 1. So there's that y, there's nothing in front of it, so we could easily get that y by itself. I have a 22, I'll subtract 4x.
And if you wanted to write negative 4x plus 22, that's fine.
Then, now that we have the equation, one of the equations solved for a single variable, we'll do what we did in number 1. We're going to substitute, take that stuff, plug it in there for x.
No, y.
I mean for y, thank you. Plug it in for y, goodness. So we have 7x minus, replace the y with 22 minus 4x is equal to 16. So we have 7x. What are we going to have to do here to get rid of those parentheses? Distribute that negative 2 times 22 is a negative 44. What about negative 2 times negative 4x? Positive 8x, so plus 8x equals 16. Let's combine the x terms. 17x plus 8x.
7x.
No, 7x plus 8x is, so we have 15x minus 44 equals 16. There's really only one sensible next step. What is it?
Plus the 44.
Plus the 44. 16 plus 44. That gives me a nice round number 60. What do I do then?
Divide by 15.
Divide by 15 to give me x equals 60 divided by 15 is 4. That means that these lines are going to intersect in one point of intersection where the x value is equal to 4. So we're going to have an ordered pair. Here's what our answer is going to look like. The x value is 4. There. How are we going to find the y value? Plug it in and plug it into the equation that's already isolated for the variable you're trying to solve for y. So you have y equals 22 minus 4 times 4. What do you mean? Oops.
I don't know.
Okay, I'm going to move that. I'm going to remove that mouse from you.
Oh.
Okay. Don't make me have to take your mouse away, Tony. I'll unplug it. I don't think I won't. So we have 22 minus here 16, 4 times 4. 22 minus 16 gives me a y value of 6. So there's the point of intersection. 4, 6.
And before I type it in, this is a good point, a place to mention that you can check your answers without actually typing them in. If you plug a 4 in for x and a 6 for y,
so you plug in 4 here and 6 here, what are you going to get on the right-hand side? What had you better get? 22. If you plug in a 4 here and a 6 there, 28 minus 12, what did you better get? 16.
So these are pretty easy to check.
Although I always think the students, it's not mandatory to check.
Yeah, it's not.
And I think you need to be confident with your own work. So there.
Parentheses 4, comma 6. Is that it?
Mm-hmm.
Oops. 6. Now, before we go any further, we may as well mention, in case you're worrying, well, what about these other two possibilities? I'm not sure that they're ever actually going to pop up.
I'm not sure either, but they're easy to spot if they do, okay? Let's suppose you're going through all of this.
And everything subtracts out.
And you wind up with 0 equals 0. Suppose this had been a 16 here. Suppose that had been an 8x or negative 8x plus 8x. If you're going through, this is true for elimination or substitution, okay? For those two special cases, the parallel lines, let's do the parallel lines first, okay? If you go through it, everything cancels out, and you have 0 equals 0. Well, how often does 0 equal 0? It always equals 0, right? Oh, wait a minute, that's the coincidental lines.
Oh,
the coincidental lines.
Wait, why not just change it since you've written parallel?
0 doesn't equal 0, okay? You have 0 equals any other number.
0 equals 3. 0 equals 7. If that happens, when you're everything, all the x's and numbers subtract out.
Except you have 0 on one side and some other number, not 0. Any other number except 0. Like 0 equals 7 or 0 equals 3. How often does 0 equal 3? Never. In which case, the lines never intersect. There's no solution. You're looking at parallel lines. If the x's cancel out and you wind up with 0 on one side and something other than 0 on the other side, you're looking at parallel lines. Now the coincidental lines, I've got to make a note. This is parallel. Although I guess those look pretty parallel to me. The next one, coincidental. The one line on top of another line. One line on top of another line. That's when everything cancels out. Then you wind up with 0 equals 0. How often does 0 equal 0? Always. That means those lines always intersect, in which case there are infinitely many solutions.
And I don't think that's going to happen anytime here.
But who
But
knows?
since it does give you those options, how do you know it's not one of these? Trust me, if it happens, you'll know it. Everything subtracts out, okay?
There's
no
no variables
variables, okay?
Number 3.
So wait, I'm going to make sure everyone got all your little things that
Now,
that
two
we've already
special
told them they
cases.
don't really, it's not going to happen in problems, but still.
And then okay,
Number-
if you're able to get a variable equals a number, then that's when you have the 1 point of intersection,
So,
which is the most common situation.
so if it's a special case, it would have to be a 0.
You'd have to
Yes.
have something like a negative 8x plus 8x. It goes to 0x. And then on the other side, collect all the other numbers. If it's a 0, infinitely many solutions. If it's not 0, you have 0 on one side, but not a 0 on the other side, something that's not equal to 0, then I don't like that statement there. I like the way I wrote it here. 0 equals any number except 0. That's when you're looking at parallel lines with no solution. Any other questions? And maybe I should have written here, reminded y'all with parallel lines, no solution. Any other questions there? Number 3.
This is the other method.
Other method,
elimination.
the one that I like. Okay.
With elimination, you add the equations vertically.
So you have to have like variables aligned.
The x's need to be lined up, and the y's need to be lined up.
Negative x plus 7y. Okay.
Written it down.
Okay, with elimination, you have to have like coefficients for like variable, for one pair of like variables, but with opposite signs. I claim we already have that. Notice we have the like variables aligned, the constants on the other side. Now, for y's, notice those things are not the same number, but for x, I don't see a coefficient in front of x, so what's that number assumed to be in front of x? And down here, -1. So you need the same coefficient but with opposite signs. In that event, you add the two equations together. 1x plus a -1x, what's just happened to the x terms when you added them together? They're eliminated. That's the reason for the name. X minus x, we have no x's remaining. Well, 9y plus 7y, that's 16y. 28 plus 20 gives me a 48. And look at that, we have a nice equation. We already have the y terms combined. All we have to do is divide by 16. And that says that these lines are going to intersect at an ordered pair where the y value is
3.
48 divided by 16 is 3. So you know at this point you're going to have a solution and the y value will be 3. Well, how are we going to find the x value? Realize we're not going to do a pure elimination. If we were going to do pure elimination, I'd say, okay, I need these numbers to be the same but with opposite signs. Well, I can multiply up here by -7 to get a -63. I can multiply down here by a +9 to get a +63. That's what we would do if we were using pure elimination. What we're really doing is we use elimination to find one variable, but what do you think I'm going to do to find the other variable? Substitution. We use a combination of elimination and substitution. And so if you think about it, my favorite method isn't really elimination. It's
not pure elimination.
It's not pure elimination. It's elimination with substitution. So I use both of those methods to solve the thing rather than just pure elimination. But we're going to substitute a y value of 3. Oh, we have it right there. Which equation do you think would be easiest to plug into? My advice is it doesn't matter. You can use any one you want, but use the one that has the fewest negatives maybe. So if we're trying to solve for x here, I think the first one would be the easiest. Down here we'd have to deal with that -1 in front of x. So I'm going to plug into that first equation. That's going to give me x plus 9 times 3 is equal to 28. Oh wow, it couldn't get much nicer than this. So we have x plus 9 times 3 is 27 is equal to 28. Those teachers that say they won't use this method because the numbers, they can't control the numbers and it could get so messy. This isn't, but Pearson knows that. They know they don't want you to wind up having to plug in 43 over 117. They know that, and it's programmed that way. We couldn't get a much nicer x value. What is it? 28 minus 27 is 1. There's my single point of intersection, 1, 3.
The C's, 1, comma, 3, parentheses. Check it. And before we go on, I don't need to write this down. But continuing the discussion that he's mentioned about these special cases, if this had been the problem, x minus 7y equals 28, and negative x plus 7y equals 20. What would happen right here if you added vertically? Yeah, the x is gone, the y is gone, so we have 0 equals 48.
How often does 0 equal 48? Never. That means the lines never intersect.
And you would choose, and again,
Parallel.
there's no solution.
Switch over.
Okay.
We got 0 equals a number other than 0, so they're parallel lines, no solution. Okay.
And again,
I hate to say it, the 2 special cases are the easy cases. Right off, everything subtracts out. There's no plugging back in to try to find the other variable. As soon as that happens, you know it's either infinitely many or parallel lines. So not having those special cases, we're not really doing you that big a favor, I suppose. They're not really. I didn't program it. So, but number 4.
See, if you wanted to use substitution on this one, you could do that. There's nothing, it's just going to be very, very messy. Why do we say that? Why am I saying substitution would be messy?
Well, 9x minus 4y equals a negative 61. I guess they could solve for x by moving the 4y over and dividing by 2.
And that wouldn't get you any fractions. You're right. So,
but it would still be messy. So,
whereas elimination, it just works so nice.
I like to think.
Back,
Okay. So, to use elimination, we need the same coefficient for like variables, but opposite signs. Look at these y's. A positive 4 and a negative 4, tailor-made for elimination. So, we'll add the two together. And you see why I like elimination. I mean, this elimination is, as soon as you do this step, you know whether you have one of those special cases. Okay, as soon as you do this step, 2x plus 9x, that's 11x. Okay, we still have an x, so it's not one of those special cases. When we add the y terms, 4y minus 4y, what's that going to give us? What's going to happen? Okay, we've eliminated the y's. 6 plus a negative 61 is going to give us a
Negative 55.
And so to solve for x, all we have to do is,
Divide by 11.
okay, to give us x equals negative 55 divided by 11 is negative 5. So we now know these two lines are going to intersect at an ordered pair where x is negative 5. What are we going to have to do to find y? Substitute. Which one do you want to substitute into? Which equation? You'll get the same answer at the end, but which equation do you think would be the easier to substitute into?
I use the top equation.
I'd use the top equation. Not only are the numbers smaller, but there's no negatives in it. So you substitute into that top equation 2 times negative 5 plus 4y is equal to 6. 2 times negative 5, that's a negative 10, plus 4y is equal to 6. I'd add 10 to both sides to give me 4y equals 16, and then divide by 4 to give me y equals 4. So we know if we were to graph these two lines, they would intersect at the ordered pair negative 5, 4. Any questions there?
Negative 5.
There's one point of intersection. And once again, in order for a special case to pop up, switch over to my paper. In order for one of those elusive special cases to pop up, it would happen right off. The variable would cancel out. All the variables, both the variables would cancel out. And you'd wind up with 0 on one side. What have you got on the other side? If it's 0, they're parallel.
No, if it's 0, they're coincidental. 0 equals 0.
Oh, you're right. Yes, I keep saying the wrong thing. So,
If it's non-zero, parallel.
number 5.
Next question.
Suppose you want to use elimination, but you don't have like coefficients on a pair of like variable terms. This is number 5. 10x plus 3y is equal to negative 13, and 3x minus y is equal to negative 2. I wrote too big here. Because I'm about to have to do something, I would have liked to have written it right here, but I don't have enough room for that. So when I look at
Oh, they
these,
can't see.
Oh.
They can't see what.
yeah, I would have liked to have written what I'm about to do right here, but I didn't leave enough room, so I'll have to, because I wrote too big, so I'll have to write it down here. When I look here, the like variable terms are aligned. I have the constant terms on the other side, so it's in the form I need, except we don't have the same coefficient with opposite signs. Here we have a 10 and a 3. Here we have a 3. Hey, we have a negative at least. What's that number that's not shown there in front of that green Y?
1.
1. Here's the trick. I can change this to a negative 3 by multiplying through by 3. The first equation is going to stay the same. 10x plus 3y equals a negative 13. Remember, when working with equations, you can multiply both sides by anything you want to and not change the equality. Well, you can't multiply by 0. You can't decide, oh, I'm going to multiply 3 by 0, because then you get 0 equals 0 for everything. So it's perfectly fine to multiply 3 by 3. Realize you're going to have to distribute it. So that's going to give you a 9x, 3 times a negative y will give us a minus 3y equals, what have we got on the right-hand side? Negative 6. (10x plus 9x is 19x. What's about to happen to the y's? They're eliminated. 3y plus a negative 3y. Negative 13 plus negative 6, that gives us a negative 19. There's only one thing to do to solve for x. Divide by 19. And that's giving us x equals negative 1. So we now know these lines are going to
guess. Don't guess infinitely many solutions or
no solution.
No
You
solution.
know there's going to be a single point of intersection, and it will occur when the x coordinate, notice I'm writing the negative 1 first, because remember ordered pairs go in the way, in the order x, y. So that's why I put the negative 1 as in the x position. What will we do to find y? Okay, well, which one do you want to do? You want to do the first one or the second one? It doesn't matter. I think I'm going to do the first one.
The numbers are a little bigger, but that negative in front of
there. So that's a 10 times a negative 1 plus 3y equals a negative 13. 10 times negative 1, that's a negative 10, plus 3y equals a negative 13. There's really only one sensible next step. To get y by itself, what do you think I'll do? Add 10. That'll give me a 3y equals negative 13 plus 10 gives us a negative 3. And then, okay, to give us y equals negative 1. Oh, well, in this case, x and y are both the same number. That can happen. Doesn't happen that often, but it can happen. Those two lines intersect at the ordered pair, negative 1, negative 1. Any questions there?
Parentheses, negative 1, comma, negative 1, close.
Now, switch to my what you call it, the camera. Okay, now we're going to look at matrices.
That's the plural of matrix.
A matrix summarizes the coefficients and constants of a linear system. For our purposes, I think I'll write just a real general definition. It's a rectangular arrangement of numbers. A rectangular arrangement of numbers. And remember that all squares are rectangles, so you could have the matrix that looks like a square. It's called a square matrix. Here, we generally enclose a matrix in brackets like we use on a number line for closed circles. Let's see. There. Here's an example of a matrix. 7, 4, -8, -8, 10, 3. That's an example of a matrix. We're just summarizing numbers in a rectangular format. Some terminology. The horizontal arrangements are called rows. So this is row 1 and row 2. The vertical alignments are called columns. Column 1, column 2, and column 3. Column 1. I'm writing COL just as an abbreviation for column. The size of a matrix is given using its dimensions. Just think of a rectangular room. You're trying to give the dimensions of the floor space. You don't say, oh, this rectangle's dimensions are 7. You give it in terms of length and width. Likewise, for a matrix, you give the size based on the number of rows by the number of columns.
Now, you don't actually multiply. That's not a times, that's a by. Like if you say you have a 12 by 15 room. Okay.
So in this case, we have 2 rows. This matrix would have a size of 2 by 3. If these numbers are equal, if the number of rows are equal to the number of columns, we call that a square matrix. In this case, it's not a square matrix. And an augmented matrix. An augmented matrix will summarize the coefficients and constants of a system of equations. I'll say summarizes the coefficients and constants. To set up an augmented matrix, you need the equation the same way you would if you were going to use elimination. You need the like variable terms aligned on one side. You need the constant terms on the other side. We're not doing that much with augmented matrices. We're going to work with square matrices in a moment, but all we're really doing is just setting up and interpreting augmented matrices.
This will not be the hardest. Number 6 is not the hardest problem we're going to have done this semester.
As a matter of fact, it might be the easiest. It's something I don't even think we need to write down. Notice with an augmented matrix,
We should write it down so
Maybe
we can
we
label
should.
the X column
I
and
like
the
that.
Y column.
Yeah, this is number 6. Let me write down that system of equations. -3x and 8x, and that's a plus y and a minus 7y equals, in my column of constants, 8 and 2. Okay.
Here. So to write the augmented matrix,
To create an augmented matrix, you have to make sure like variables are aligned, the constants are on the other side. There are 2 equations, so we're going to have 2 rows. Let me write my little brackets. Let me write my brackets. There
Why don't you write the
and
equal
there.
sign first?
To represent the equal sign, we don't put equals inside this matrix. We put a vertical bar. That vertical bar is representing the equal sign. You'll have a column that summarizes the x coefficients. You'll have a column that summarizes the y coefficients. And over here on the right, those would be your constants. We can fill that in right now. 8, 2.
I think you could fill it all in right now.
The coefficients for x are -3 and 8. The coefficients for y are, hey, I don't see a number in front of this. What do I assume the coefficient is? So we have a +1 and a -7. Do they ask for the size?
No.
Oh,
They used to, but I
they
don't think
used
they
to.
do anymore.
Okay, well,
Yeah, here it's just, you see, that's why I was tempted at first to do it without writing anything. Just go through -3, tab 1, tab 8, tab 8. I'm hitting the tab key to move through without having to move the cursor every time. Remember that one semester I was there saying tab and you said, that's very annoying. Stop saying tab.
oh my
Okay.
goodness.
Mm-hmm.
You know, I think we can do this. Y'all just watch it. Y'all
Oh,
can
well,
tell me.
y'all call it out. I'm going to start right here in this spot and tell me the numbers I'm going to
Well,
type.
first of all, notice that it's already arranged in the format that you need. You have the x's aligned, the y's. Here, there's 3 variables, the z's, and you have the constants on the other side. So let's fill in the first row. The first row summarizes the numerical data on equation 1. So filling in the first row, we have the coefficient
I'm
for
getting them
x,
started.
8, and then -8. Be sure to use the sign. 8, and my constant. Okay. Now we go down to the second one.
8,
-8, 5, and the constant. 9.
No. Oops. I went too far. 0. Good. Do y'all see why it's 0 and not a 1?
The third row does not have an x variable appearing. So the coefficient for that x variable is 0. 0 times x is 0.
If it had just been an x there, then that's when you put the 1. Okay?
There's no x appearing there.
Mm-hmm.
The y coefficient,
6, -6, and -2.
in Math 1324 and in linear algebra, we take augmented matrices and we get them in reduced row echelon form. There's a series of elementary row operations that are anything but elementary, okay? But
the TI graphing calculator handles it
really nicely, okay, you're right.
Yeah,
but if you're doing it all by hand, it really gets messy. Fortunately, we don't have to do that, okay? But
there's some nice applications.
you can take a matrix that looks like this and, this isn't the one, I'm getting ahead of myself. So
in algebra, we always do it one way and then do it in reverse. Could y'all do this one in reverse? Here's the matrix. See, like
now they're going backwards. They've given you the matrix. You have to write the system of equations. So
what goes here? 5. Let's see how we're doing this.
I don't know if I really like that because they have that minus there, so be careful.
Well, okay, minus.
They already have the minus, so don't type a -2. You have just the 2.
And right there, 2. What will I type in this spot here? 9.
Notice there's a 0 for the x spot. There's no 0 in the second equation.
And look, they've already done the minus z equals -6. What about down here? 4. Notice they don't have it. They're just skipping right past the y. It sort of looks ugly because the way they don't have the like terms lined up, but I'm not going to complain. This would be a 3 and a 7.
Well, you said it sort of looked ugly. That sounds like a complaint to me.
No.
You're going to not complain anymore.
Okay. Now, as Tim was mentioning a while ago, that there's a way to take these matrices. It's a real nice little feature on the TI graphing calculator, and most graphing calculators handle it, where you enter this big old matrix, and it'll shuffle it around and until it looks like that.
Ones down the diagonal, zeros above and below those ones, and then constants by themselves on the right-hand side. Why is this reduced row echelon form desirable? Think about it. I'm going to write this down, okay? This is number 9.
Are you seeing what you're going to have here?
I think so. That x equals 2.
Uh-huh.
6.
This 2, 6, 1. Okay, yes.
If we went and did what he was doing on the previous one, why don't you go ahead? It says use X, Y, and Z as the
They have to
variables.
tell you what variables to use. They're saying to use X, Y, and Z.
See right there.
So what is this first row saying? Why is this reduced row echelon form so nice? Once you have that 1 there, that says 1x. What about the y and z? 0y plus 0z is equal to 2. When you get the matrix in reduced row echelon form, wherever the 1 is, the number on the other side is the solution to the system of equations. So x is equal to 1.
No, 2.
I mean, x is equal to 2. What's the second row saying? So we have 1y, so y is equal to 6. And what's the third row saying? Z is equal to 1. So taking an augmented matrix and getting ones down the diagonal, zeros above and below, that's called reduced row echelon form. If you can do that, then these numbers over here on the right are the solution to the system. And we see that in detail in Math 1324 and linear algebra.
So right here, what am I going to do? I'm just going to type X, Y, and Z. X is 2, Y is 6, Z is
Notice it
1.
says simplify your answers. Technically, don't write this down, but technically we'll look at that first row. That's saying 1x plus 0y plus 0z is equal to 2.
They don't want
you to write that. That's what they mean by simplify your answers. I remember a student asking, what do they mean simplify? Well, they don't want this long form here. The 0y times 0z is just 0. 1 times x is just x. Any questions there?
Let me see. I didn't check it, but I'll check it now.
Well, you got to check it or I don't get credit.
I know, but this way they'll feel more confident. Okay.
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 Switch over. I got to do a little talking.
We're going to find something called the determinant. What we're working towards is
a method of solving linear systems other than elimination and substitution that uses that uses matrices.
Like this one here, like number 13 says solve using Cramer's rule. Well, there's 2 other methods you could use. Do y'all want to tell me
what
what
are the
they
other
are?
2 methods you can use to solve a system? Substitution or elimination. I guess elimination wouldn't be that bad. We could get a 6 here, a -6, by multiplying the first row by negative 2.
But we're going to have a method that would work if it's messy fractions. Suppose you got x equals negative 11 over 654. You don't want to have to plug that in. But Cramer's rule is a nice way of doing it that
it's numeric. It's only numeric. Numeric calculations, no variable manipulation, and that's what we're working towards. But
it's
in
going
order to do that, we need to discuss
something called
determinants.
determinants. So, what are you going to say?
Determinants are a unique number assigned to square matrices.
Those augmented matrices we were working with, those aren't square. We have 3 rows and 4 columns.
I guess for the 2 by 2, I'm going to go ahead and write out the definition. If you take a linear algebra course, you'll see that determinants have many of the same features as absolute values. So the notation that's used for the determinant of a matrix, notice normally we enclose a matrix in brackets. But if you want a determinant, the notation for determinant, look at that problem number 10. It looks like big absolute value bars. And the reason they use that notation is because there's a triangle inequality for absolute value. It applies to matrices as well. Many of the properties of absolute values can be applied to the properties of determinants. So switch over to my paper. I'll go ahead and write a 2 by 2 determinant definition.
This is how you define, this is how you're going to do that number 10. How do you find the determinant of a 2 by 2?
2 by 2 means there's 2 rows and 2 columns. So let's suppose that the numbers in the matrix, row 1 has AB, row 2 has CD. It is the difference of the cross product when you start in the upper left-hand corner. You go,
well, that makes it clear. Right
AD. I thought that was a pretty intelligent statement. You multiply A times D minus B times C. It's the difference of the cross products when you start in the upper left-hand corner. You don't go BC minus AD. If you do that, you'll get the wrong answer every time.
You got to start with that first number.
That's right.
Mm-hmm.
So going back to number 10.
Oh, wow, this is neat because you have room to do number 10 and that
Right.
little bit of paper
I know.
you have there.
Okay, so it's 3, negative 1, and negative 8, 8. And there's my determinant bars. Equals. You multiply. You start at the 3. 3 times 8 is 24 minus, now the other diagonal, negative 1 times negative 8 is positive 8. So 24 minus 8 gives us a determinant of 16.
So will this only work for square matrices?
Only the
It's
square.
only for square matrices.
Mm-hmm. 16. Now, for the little 2 by 2, you just do the little cross multiply. But for 3 by 3,
I guess for time I'm going to write out the definition. Y'all want me to write out the definition of the 3 by 3 determinant, or just show you how we find it?
oh wait, I'm going to give it.
Oh, I'll show you. Here, let's see. Here it
Here's the
is.
definition from last year.
Yeah, I always write it out. There it
Okay,
is.
there it is. AEI
Well,
plus.
wait a minute. You
Oh.
see a 3 by 3. There are 3 rows and 3 columns. This E is just an arbitrary real number. It's not a definition, and it's not the natural exponential. The I is just an arbitrary real number. It's not the imaginary unit, the square root
F
of
is not
negative 1.
function.
It's A times E times I plus B times F times G plus C times D times H. Close the parentheses, minus C times E times G, A times F times H, B times D times I. The trick for finding a 3 by 3 determinant is to rewrite the first 2 columns. There's just a lot more diagonals in a 3 by 3 determinant than a 2 by 2. With a 2 by 2, there's only 2 diagonals. With a 3 by 3, there are 6 diagonals you have to take care of. So looking at number
I
11,
think for number 11, why don't you do the example, and then if they want you to write it out like that,
that formal
Okay.
definition I will.
But
This is number 11. Okay. And we're going to find the determinant of this 3 by 3 matrix. The first column is 2, negative 3,
no, right in the
3.
column. Oh,
The second column is 1, 2, 5. The third column is 3, 1, negative 6. Make sure I didn't miscopy. One minor mistake can really throw the answer off. Okay, let's switch over to my paper. We're trying to find the determinant of a 3 by 3 matrix. The first thing you do, recopy the first 2 columns. That 2, negative 3, 3, you write it beside here, and the 1, 2, 5. You're going to have a big set of parentheses minus a big set of parentheses. Just like with the 2 by 2, you must start in the upper left-hand corner.
the first number.
The first number in the determinant, that's where you start.
Don't start here.
You multiply. 2 times negative 6. That's a negative 24. Then you move to the right and you go down the next diagonal. 1 times 1 times 3. What are we going to get there? A positive 3. The last diagonal, 3 times negative 3 times 5.
3 plus negative 3.
Minus
is
45, I agree. Now, you're going to move, you're still positioned at this 3. You're going to change directions. You had 3 diagonals falling from left to right. Now you're going to have 3 diagonals falling from right to left. You're still positioned at this 3. 3 times 2 times 3 is 18. Oh, I'm getting messy. 2 times 1 times 5 is
You'll call that
10, I agree. 1 times negative 3 times negative 6. That's going to give me positive 18. I agree. You have 3 diagonals falling from left to right, minus 3 diagonals falling from right to left. To see all of the diagonals, you have to recopy the first 2 columns. And now simplify inside the parentheses. Negative 24 plus 3 is a negative 21. Negative 21 minus 45, is that a negative 66? And this minus here, that's the minus from the definition. You connect the cross products by minus. Well, what are we going to have here? 18 plus 10 is 28. Plus 18, is that a 46? Negative 66 minus 46, is that giving me a negative 112 for my final answer? Any questions?
Sort of see the pattern there. Just make sure, if you start with the 3 times 2 times 3 first, you're going to get it wrong every time. You must start with that first number. First number up here is this one right there. And I'm just trying to come up with a way to, so you'll remember, you start here, not there. Okay.
Any questions?
Oh, they want me to punch it in so you'll see it's right. Negative 112. Oops. Here's
another one. Think about how we're multiplying. If you want ease of multiplication, what one number would you like to see a lot there? What's the easiest number to multiply? One is okay, but there's another one that's easier. Zero. Because if you have a 0 anywhere in the diagonal, the product is 0. So here's number 12.
It's a nice one because there's 2 zeros. That's what he's saying there.
We have 10. Okay.
Yeah, not miscopied it. So.
What will I do first?
Copy the 2.
Mm-hmm.
Okay. First column, second column. And you laugh when I say this, but you've got to be careful when you're recopying those numbers. There's so many places just dropping a negative or accidentally adding a negative. That'll certainly mess up your answer. Okay. It's parentheses, big parentheses, minus big parentheses. Here we go. We're going to start 10 times 7 times 0 will give me 0. Negative 4 times 0 times 10. Another 0. 7 times 3 times negative 4. 21 times negative 4, is that a minus 84?
The numbers are really large, you might want to use a calculator.
Now we go in the opposite direction. Let's see, how about a blue? Okay, 7 times 7 times 10. 7 times 7 is 49 times 10, 490. But the next two products, these are nice. 10 times 0 times negative 4. 0. What about the last diagonal? I agree. Simplify inside the parentheses. We have negative 84 minus 490. That's going to give us a negative that's a 4. Negative 574 for my final answer. Any questions? It didn't happen here, but it could certainly happen on y'all's. Be careful. This second number here may turn out to be negative, in which case, when you combine it with the negative from the formula, what's going to happen? It's going to be changed to a positive, so be careful. Both of these It just so happened this second number was positive. It may be negative. And so you'd have a minus and negative, that becomes a positive.
So negative
574. Once again, this is something we could have done at the beginning of the semester. Okay, Cramer's rule.
This is a third method. Instead of elimination and substitution, we're going to show you X.
I'm going to define Cramer's rule to be a method of solving linear systems that uses determinants. It's a method of solving linear systems of equations that uses determinants. Cramer did a lot of important research study in matrix theory, and it's sort of funny. I remember it's something he's remembered for is Cramer's rule, and he didn't think it was that significant when he proved it. Okay, but it's the thing that
rolling
gets
over in his grave right now. I can't believe
that's what I'm remembered for. So
write it out. X equals D subscript X.
okay. X is equal, let's suppose that your system has two variables, X and Y. X is equal to D sub X divided by D, and Y is equal to D sub Y divided by D. Well, that doesn't say much, does it? What is this D sub X and this D? Okay, I'll show you an example. It's actually it's not difficult. It's very...
So let's flip the page.
Okay.
This is another one of those things I don't think we want to write out. I think
we don't want to write out the individual steps.
I tried to write out a recipe last year, and it didn't work.
I mean, you wrote it out. I think it was as muddled as, muddy water, but still.
Yeah, I mean, it didn't add anything. It's just like the AEG plus BFI doesn't add anything to it.
4x plus 3y is equal to 5, and 7x plus 6y is equal to 7. Remember, determinants only work for square matrices. Here's what Cramer did. The first thing he did was he found the determinant of just the coefficient matrix.
He just loved working with numbers, and he discovered a pattern that I don't know if anyone would have ever discovered.
Okay, the coefficients for x are 4 and 7. The coefficients for y are 3 and 6. And now that's a square matrix. He's ignoring the column of constants, okay? He's ignoring the column of constants. It's a 2 by 2 determinant. Doesn't get any easier than that. Cross multiply. 4 times 6 is 24. What is the formula? What sign do we use next? According to the formula.
Your little, you may have forgotten.
For a 2 by 2, we multiply. What's the sign? Minus. Multiply. 3 times 7 is 21. 24 minus 21 gives me a D value of 3.
So what Cramer said is, take just those coefficients, and this is instead of elimination or substitution. Just do the little crisscross.
And find the determinant of the coefficient matrix. Next, he formed however many variables there were, in this case 2, so he found D sub x. D subscript x is the determinant you get when you replace the subscript column with the column of constants. So d sub x, you replace the x column with 5, 7. The y column, you leave it as 3 and 6.
Again, he loved working with numbers, and he figured this out.
Multiply, that's 30, minus, that's from the formula, multiply is 21. 30 minus 21 gives me 9. We found all of these determinants. For each variable, there's a subscripted determinant. So now we have to find d sub y.
Whatever the subscript is, that's the one you replace.
Start back at d. You look at d. In this case, the x column is back to 4, 7, the original values. You only replace one column at a time. The y column, he replaces with the column of constants, 5, 7. 28 minus 35. 28 minus 35 gives me a and then a negative 7.
Now show them your little statement of what the Cramer's rule.
Cramer's rule said
Down here.
x is equal to d sub x divided by d, y is d sub y divided by d. Now that statement is significant. X is equal to d sub x divided by d. D sub x was 9 divided by 3. Gives me an x value of 3. So these lines are going to intersect when the x value is 3. Y is equal to d sub y divided by d. D sub y is a negative 7 divided by 3. Well, I guess that's it.
And that gives you a hint of why
thirds.
they thought, wow, Cramer became famous, because imagine if you were doing this with elimination and substitution, no calculator, and all the answers were turning out to be fractions, like negative 11 over 65. You don't want to have to be plugging that in to find the other solution. So here's a way that you can find it, even if both of these answers had turned out to be messy fractions. But so what? Well, that was the thing that I think made him so famous.
Also, from a programming point of view, when the first generation graphing calculators that came out that solved linear systems of equations, this is the method that they had programmed.
It's real easy
It's
to
all
like.
just numbers. There's no, okay, now we got to combine the like variables, got to move the
plug this
constants
over
over here
here,
and
yeah.
stuff.
No.
It's very easy to program from a programming point of view. Okay, type in the answer.
It is
3, comma, negative 7 thirds.
comma, negative 7 thirds. Make sure you don't put the parentheses right there. I'll hit the right arrow to get out of that denominator, and then I'll put my parentheses.
Well, let's do another one. So we now have a third method of solving linear systems, in addition to elimination and substitution. Number 14. Okay. Now suppose you're taking a test and you use elimination or substitution to solve the system. Am I going to know it? No, I won't know it.
But as long as you get the right answer, I mean, what you have here are three techniques that you can use: elimination, substitution, or Cramer's rule. Use whichever one you do best, or whichever one you think is going to be
big
easier.
numbers, and you think, oh, this is going to wind up with the messy fractions. Messy fractions as answers. Cramer's rule is better. Okay, because notice we didn't wind up with a fraction in the previous problem. We didn't wind up with a fraction until that final dividing step. Okay, first of all, the determinant D. D is just the coefficient matrix.
I wonder if one of those videos has me trying to write out
2, 7,
instead.
and then the Y column is 5, 6. Here we go. Multiply. Multiply. Minus. Multiply.
Oh, they know 35. They're just not speaking to him.
Gives me a negative 23. Then we find D sub x.
Place the 2, 7. With
The 2, 7 is replaced with the column of constants 10 and negative 11. The Y column stays the same here. It's only the X column that's replaced. That's going to give me a multiply 60 minus.
Oh, this is going to be good.
Finally, multiply. What's that going to give me? Negative 55. This is what I was talking about. Remember, you have that negative from the formula. That second cross product is negative. So that's to become a positive. Is that a 115?
Any questions?
Now D sub y. What numbers are in the first column? 2 and 7. It goes back to the original variables. I mean the original values. You don't leave the X column as 10, negative 11. You only have only one column has that column of constants, and whatever that subscript is. That's a Y, so the Y column gets the 10 and negative 11 now. That gives me a negative 22 minus, what are we going to have there? 70. Negative 22 minus 70 gives me a negative 92. I was thinking for sure we were going to have messy fractions as our final answer because of that 23.
But no.
But I don't think so. Look what's about to happen. Whoever programmed it did y'all a favor. X is D sub x divided by D. D sub x is 115 divided by negative 23. What's 115 divided by negative 23? Negative 5. So these lines are going to intersect when the X value is negative 5. Now Y. Y is D sub Y divided by D. D sub Y was the negative 92 all over negative 23. Negative 92 divided by negative 23 goes in very nicely to give me a positive 4. So there's the point of intersection. An easy,
what was it? Negative
5, 4. From a programmer's point of view, it is a very easy process to program.
We're just looking at numbers.
Numbers, multiplying and subtracting and dividing.
Mm-hmm.
You never have to go and get I got
Combine
to
like
distribute, I
terms.
got to
Distribute.
combine like distribute, combine like terms. So I better remember to distribute through that negative, move that term over and change the sign.
That's
Just
just
an
numbers.
easy programming process. Any questions there?
And y'all have been asking for it, so finally,
Here's some good word problems. Number 16.
we'll go back and do 15 last. For some reason,
It's awkward. It's just awkward, the wording.
mhm.
You have your 1-point shot and your...
By the time you
whatever.
see the pattern on these, number 15 won't seem so awkward.
Maybe I'm the only one that thinks they're
I don't know.
awkward,
I just
okay?
think the wording is strange. But oh,
A
God.
woman bought some large frames for $19 each and some small frames for $7 each at a closeout sale. If she bought 27 frames for $285, how many of each type? Find how many of each type she bought. And I think these are picture frames.
Yeah.
I used to think they were, frames for glasses, but I
why
think they're
would she
picture
need to
frames.
buy 27 frames, glass frames? So it's got to be.
Well, why would you need to buy 27 picture frames?
Maybe she has
owns a
27
gallery?
pictures.
Oh, okay, so it's 27 pictures.
Mhm.
Okay, number 16.
These word problems, don't let them freak you out. There's nice pattern for setting them up, and you sort of have an idea you're going to want to write two
If there are
equations
two
like
there,
this.
and generally, if you took a more detailed course on matrix theory, you would see that for a system of equations, if you want a unique solution, the number of variables should equal the number of unique equations. So if you have two variables, you want two equations. If you have, let's say, three variables and only two equations, you're not going to get just a
An
unique
answer.
solution, okay? So,
You're going to get one of those infinitely many things, so why would you want that? It wouldn't make any sense, okay? If the answer here was, oh, well, she bought infinitely many large frames, that doesn't make any sense.
a woman bought some large frames for $19 each and some small frames for $7 each. She bought a total of 27 frames. Find how many of each type she bought. What are our unknowns? Switch over to my paper, Tony. I'm going to write down, there are two things we don't know. What are the unknowns?
What are we trying to find? It gives you a hint. Right up here, she bought blank large frames.
So we're trying to find out how many large frames she bought. What
What's
else?
the next thing we're going to
The
find?
number of small frames.
Okay,
So we have large frames
Write down the two unknowns that you're looking for.
and small frames.
And since we don't know, it's asking how many large frames.
So the thing we don't know, that's the quantity. I'm going to put an X and a Y. I have a little column there for quantity.
We don't know how many large frames she bought. We're calling it X. We don't know how many small frames she bought. We're calling it Y.
Well, she had to tell us more stuff than that. But
Yeah.
notice how many times I'm rereading the problem. I keep going back, filtering out information. It looks like she's telling us the selling price or the purchase price. She switch here, so this is the
19
price.
for large.
She paid $19 for each large frame and $7 for each small frame.
All right, 19 and 7. Okay. Now, if these are going to be systems of equations, we've got to have an equals and a number. Okay?
I think they gave us some totals here as
Did they
well.
give us some totals? Let's see.
She bought 27 frames. 27 frames. Switch over here. We're going to put some totals.
Draw equal lines here and here.
Okay. There and there. If you total the number of large frames and the number of small frames, that had better give us what? 27. Well, we know that the Each large frame sold for $19 and each small frame sold for $7.
Do we have a
do we have a
dollar?
total dollar amount that she spent?
285.
$285.
Now,
We have two unknowns. We need two unique equations. I'll get us started. If you take the X large frames and you add it to the Y small frames, what had that better equal? 27, okay. Now, this next thing, she said, we need to think about this a little bit. She paid $19 for each large frame. Suppose she bought 10 frames. Suppose she bought 10 large frames. How much money did she spend on all of those large frames? Just the large frames.
if she bought,
You go price times quantity. 19 times 10, she spent $190. So you go price times quantity, and that'll give you the amount of money she spent on all the large frames, 19x. 19x is the amount of money she spent buying the large frames. How much money did you spend buying the Y small frames?
7Y.
Okay, you go price times quantity. That 19x is all the money she spent buying the large frames. The 7y is the money she spent buying the small frames. The large frames plus the small frames, we know how much she spent total, $285. So,
at this point, it's up to them.
elimination, substitution, or Cramer's rule.
But since you're the one doing it, it's really up to you. What are you going to use?
What's my favorite method? I told you at the beginning I had a favorite method for solving these systems. What is it?
Elimination.
It's not substitution. It's really elimination with backwards substitution.
Mhm.
We do a little of both. That's what I prefer. I guess we could use Cramer's rule.
I think use elimination.
Okay. If we're going to eliminate, well, notice we already have the like variables aligned. That's good. Well, we need the same coefficient but with opposite signs.
Multiply the top by negative 19.
Uh-huh.
You could multiply the top by negative 19, or if you want smaller numbers, what could you do?
Multiply
The top by
Seven.
negative 7.
Seven.
I'm feeling lazy. I'm going to multiply by negative 7. Did y'all hear that? We're going to get a negative 7y here and a positive 7y down there. So we'll have a negative 7x minus 7y equals, what's 27 times negative 7? Is that a negative 189?
49. So yeah, negative 189.
Is that a negative 189?
And I'm feeling too lazy to pick up my calculator, or to pull up the calculator.
And then we still have that 19x plus 7y equals 285.
Now, if you had wanted to multiply the top by negative 19,
You'd still get the same answer at the end, but here I'm getting rid of the y rather than the x. But if you did that, you'd still get the same answer.
I think you'd wind up with more negatives.
Oh, guess I'm not going to sneeze. Okay. Negative 7x plus 19x, that gives me 12x. What's about to happen to the y's? Negative 7y plus 7y. What's negative 185 plus
189.
Negative 189 plus 285? That's going to give me a positive 90. What did you say? 96? I agree. There's only one step to get the value x. What is it?
Divide by 12.
Divide by 12. That's going to give me an x equals 96 divided by 12 gives me a positive 8. Now realize, suppose you'd gone through this and you got a negative 8. Would that be okay? You can't buy a negative number of
You
frames.
can't you can't buy a fraction.
A fractional number. This thing here
That
had to be
is.
a positive integer, okay? So that means she bought 8 large frames.
So you draw a bar and write answer.
Okay, there. Answer. She bought 8 large frames. And now we know with the elimination, you then back substitute to find the y value. But I think you can just look here and think. You need 27 total frames. What does y have to be? Y has to be 19, I agree. But you could say, okay, or you could say, here's that. You could plug into either one of the original equations. I'd plug into the one that has the lowest coefficients. So you have 8 plus y is 27. So y is 27 minus 8. Isn't that what we did there to get the 19?
But I think you can usually just do this, find the other one just by
inspection.
In this column. Okay, she bought a total of 27. There were 8 large frames, so 27 minus 8, 19 small. So
Any questions there?
8 large, 19 small.
She must own a gallery.
8 large, and 19 small.
Summarize the information using a table.
This
That'll
sort of
help
table.
you see the equations.
So we're going to do number 17, and it's going to set up amazingly like number 16.
The cost to attend a movie is $7 for adults, while children are admitted for $4. If a movie was attended by 58 people who paid a total of $277, how many adults and how many children attended the movie? What are our unknowns?
And this one's nice because it tells you.
How many adults and how many?
Okay, adults
That's right.
and children,
That's what we want to know.
and we want to know how many attended, so that's my quantity. I guess I could label this column how many instead of writing out quantity. I don't know. Let me see.
You'll notice, I think all of these word problems involve dollars. This system of equations are just
lend themselves so well
to
to
financial.
financial applications.
That's why you
Let's go
spend
back. We
so
need to
much
read
time.
some more stuff.
Yeah, let's reread.
The cost. So we know how much it costs. The adult tickets cost $7, and children tickets cost $4. So I'm going to say the cost. That's $7 for adults, $4 for children, and they better give us some totals because we need 2 equations. So better give us some totals to create those equations.
What are
Hey, I see a total. 58 people. 58 people attended, so switch over here. If I add up the number of adults, there were X adults and Y children. If I total that column, that had better give us
58.
58. What about costs? Adult tickets are $7. Children tickets are $4. Oh, look at that. The total amount of money that theater took in was $277. So, if we add up all the money they took in, it should be, did I say 277?
Yes.
Is that it? I thought it said 288.
Oh,
It said 277? Just beer.
Yeah,
Yeah, you're right.
277.
What made me think it was 288? Okay. We have
pull
2
down a little.
variables.
Does it look sort of like?
Oh, we don't have our answer column yet. Give me one of the 2 equations.
X plus Y equals 58.
Okay. X adult tickets plus Y children's tickets should equal the total number of tickets sold. X plus Y is equal to 58. Okay, now our cost equation. Each ticket costs $7. Each adult ticket costs $7. They sold X adult tickets. How much money did the theater take in from the X adult tickets? In terms of X. 7X. It's price times quantity. So 7X, that's all the money they got from the adult tickets. How much money did the theater take in from the Y children tickets? 4Y. Price times quantity again. Here's all the money they took in selling adult tickets. Here's all the money they took in selling children tickets. Adding that money together, it better give you 277. Well, what method do y'all want to use? Elimination, substitution, or Cramer's rule?
I use substitution.
You're using substitution? Okay, let's use substitution.
Did you say substitution? Oh, what?
Okay, which variable are you going to solve for? You need a variable by itself, either X or Y.
I solve for X first.
Okay. In which equation, the first or the second?
Yeah,
There's
you said
only
the
one
first.
correct. Oh, you solve for X in the first? I agree. You wouldn't want to solve for X in the second, because then you might wind up with that messy fraction when you divide it by 7. So solving for X, we'll have a 58 minus Y. This is a good opportunity to remember the substitution method. And then what am I going to do with that green 58 minus Y?
X.
Plug it in for X. Plug it in for X here on top. No, it has to be in the second one. 7 times 58 minus Y plus 4Y is equal to 277. 58 times 7. Well, 50 times 7 is 350. 8 times 7 is 56. 350 plus 56, I'm getting a 406 minus here 7Y plus 4Y is equal to 277. And we know negative 7Y plus 4Y, what's that going to give me? A minus 3Y. We need that Y term by itself, so what will we do? Subtract the 406. We have a negative 3Y equals 277 minus 406. 277 minus 100 is negative 123 plus, am I getting a negative 129? And then divide by negative 3. This is going to give us a positive Y value. If we didn't get a positive Y value, what does that mean? Suppose we got a negative Y value. You've done something wrong, because there's no way they could have sold a negative number of children tickets to give us Y equals, what is that, 43? So they sold 43 children's tickets. How many adult tickets did they sell? I don't think we have to back substitute. We can just logic our way through it. We know they sold 58 tickets. 43 of them were children. So how many adults? 15. 58 minus 40.
Maybe write 58 minus 43 equals 15. Now, if you're wondering, well, wait, why you do this one different from the other one?
Because Dale said to do it
Do
different.
substitution.
Do substitution.
If you were going to use elimination.
Normally, it's like when I let our friends choose what we're going to eat. And I tell them, go right ahead. If you choose the wrong place, you can choose again.
I'm going to let them have
If we always pay.
Yeah, so
And so we always pay. So
they can
yes,
choose, but
they can choose. If they choose the wrong place, go ahead and choose again. Keep choosing. If you choose the right place.
But like you could have multiplied up here maybe by either -7 or -4. If you'd multiplied
And
the top
use
one by
elimination.
-4, that would have gotten you the same answer. Hey, I better punch this in and make sure we didn't mess up. 15 adult and 43 children. I think in the future we'll, I'm going to remember, do the ones with the
Are we going to
substitution.
do Cramer's rule
No,
next?
we're going to go back to elimination on the next one. Okay. Oh, wow, this is a...
Oh, they say use Gaussian elimination or
Ignore all of
Gaussian
that.
elimination.
No.
Ignore that. That's that process of getting
Ones
ones
and
down
zeros.
the diagonal and zeros elsewhere. We're not doing that, okay? We're using Cramer's rule, so just ignore those instructions. Use Cramer's rule or elimination or substitution. I think I'm going
put
to
in the future a hint.
Yeah, you
Don't
need
use
to.
that. Use substitution or elimination.
Don't look at view an example because they're trying to get the
really?
ones.
And
Let's see if you
zeros.
view an
Are
example. Let's see how much detail. Are they showing the detail or are they saying punch it into your calculator? There.
Oh, you see, they're going through all the, oops, I went too fast. They're going through the detail of how you rewrite everything to get the
ones down the diagonal,
Yeah,
the zeros
that's
above
too
and
much.
below.
Yeah, that's too much effort. Okay.
Mike works a total of 60 hours per week at his two jobs. He makes $6 per hour at job A and $7 per hour at job B. If his total pay for 1 week is $380 before taxes, then how many hours does he work at each job? What a downer. What a downbeat problem. He's having to work 60 hours on two jobs. You make $6 per hour at job A and $7 per hour at job B. How many hours does he work at each job? What are the unknowns?
How many hours he works at each job?
Okay, so
just like
switch
that.
over. I know.
Oh, okay.
That's what I'm going to do, but you got to switch it over. I'm going to say job A and job B.
Instead of maybe you should say hours.
I'm going to say hours worked. I guess I could use A and B. A hours at job A and B hours at job B, but it's too late. I've already written X and Y. Okay. Hey, how many hours total did he work? They gave us a total. He worked 60 hours. Where do you think I'm going to put that?
Right there.
I'm going to total up the hours worked at job A and the hours worked at job B to get a total of 60. And they told us other stuff. Oh, he's making $6 per hour at job A. So this is his hourly wage. Hourly wage. $6 per hour at job A and $7 per hour at job B.
What's that total for the dollar column?
He worked a week and he made $380 before taxes. So if we total up all the dollar amount, that's going to give us what? The 380. We have two unknowns. That means we need two equations. Give me one equation.
X plus Y equals 60.
I agree. The hours at job A plus the hours at job B had better equal 60. Now the hourly wage, $6 an hour at A and $7 an hour at job B. I remember students in the past saying he should just work at job B. Well, you can't just go to your boss and say, I want to work this many hours. In most cases, am I right? Maybe they're saying, no, you can't work more than 20 hours a week. We're hiring you for 20 hours a week. So going and saying, oh, I just want to work only at $7 an hour, That's really not an option. Give me the wage equation.
6x plus 7y
Okay.
equals 3.
6x, that's all the money, the price per hour times the number of hours that he makes at job A, plus
7y.
7y, the price per hour times the number of hours equals
3e.
the amount of money before taxes, 380. Frankly, I'm just hoping that this is cash, he's being paid cash and he's not having to pay taxes. So, having
Which
to
I
pay
guess is
taxes
against the law, but
Oh, you're
yeah,
right.
so
You're
let's just
right. I better
don't
not
sit
say
there
that.
endorsing
Tax fraud.
tax fraud.
I don't.
IRS will come at you
the
like
expressions my
Whatever you say.
opinions I make do not reflect what I would actually do or the opinion of Delmar College. Okay, so and what I'm hoping, okay, I'm hoping this, but that doesn't really make
Maybe
it
he
happen.
works in a country, what's one of those countries where there's no taxes. They make so much tax money from
Tourists?
no, from oil.
Oil.
That
Yeah.
There's some small countries where no one, the citizens there don't pay taxes for anything. They make so much money from their oil. But, okay. I'm going to use elimination. And
Which variable are you going to eliminate? Y'all tell me which one you think would be. I think there's one that might be marginally easier. The multiplication. Do we want to eliminate X or Y? What do y'all think?
multiply by -6 or multiply by -7? Which one would y'all?
I
Yeah.
think -6 would make it just a little bit easier. So we have a -6x minus 6y is equal to -6 times 60 is -360. The second equation.
Just no coffee. Yeah.
Oh yeah, we've already come up with it. I was looking at the table. I forgot we've already written out the equations, haven't we? Add the two. -6x plus 6x is eliminated. -6y plus 7y gives me. Oh, this is really nice. Just 1y equals -360 plus 380 gives us a positive 20. So, where do I put the 20? Here or here? Top or bottom? Okay, that's Y is for job B. So, he works
now
20
this is
hours at job B.
Right answer.
Oh, yeah. There's my answer.
And, oh, wow, this is bad.
Or Johnny is working 20 hours at job B. How many hours is he working at job A? 40. He has a full-time job, and he's
Still having to
still
work.
working it. Then he's working another job, earning a higher hourly income.
How do we know? And he just said a full-time job. What does he mean by that? In order to be considered full-time, 40 hours a week.
Don't say it because the person.
Oh, okay.
Okay. So
Someone we know.
Don't.
Okay. So 40 hours job A, 20 hours job B.
So poor Johnny's working 40 hours at job A and 20 hours at job B.
I'm glad that that's no longer the last problem. Now we're going to go back to number 15. 15 is a less
Downbeat problem. A basketball player scored 13 times during one game. He scored a total of 17 points. He got 2 points for each 2-point shot and 1 point for each free throw. If I remember correctly, a free throw, there's the line, and something happened and they get a free throw. Am I remembering it correctly? But you're not moving around, you're not fighting other people for the ball, so they get only 1 point for the free throws, but they get 2 points for the 2-point shots. It's the 2 points for the 2-point shots. That's what I find awkward, okay? So how many 2-point shots did the basketball player make? How many free throws? What are our unknowns? Just
Here's one of them. How many?
what am I going to write? Switch to my paper. What am I going to write as the row header?
2-point shots.
2-point shots and
Free throws.
free throws. Okay.
At first glance, you might think this doesn't seem anything like the dollar problems we've been doing, but yeah, it is.
Yeah, it is.
Oh, you drew a horizontal
I don't
line
know
there.
why I haven't been drawing the horizontal lines.
Because it's going to
like
look so
that.
awkward when you draw the equal sign too.
No, that's not going to be awkward. So that's my quantity. This player made X 2-point shots and Y free throws. So I'll say number of throws. I think I should just write quantity.
Yeah. Now, we don't even have to look at the.
Well,
The
maybe we
problem
do.
to
They
see
may
the
not
thing.
know. Look back at the problem because, well, free throws. We know that for each 2-point throw, how many points did they get?
2 points.
Points. 2 points. Okay. For each free throw, how many points? Just one. And we need some totals. I see that number 13. Where's 13 going to go? Is it going to go at the bottom of this first column or second column?
So 13. He scored 13 times during the game.
Is it going to go at the bottom of the first column or the second column? The
Mhm.
first column. Okay. So equals 13. Now the number of points. If we total up all the points, they gave us a point total. What is it? How many points did this player score?
17.
17. Give me the two equations.
X plus Y equals 13.
So see, it still sets up the same way as the
And?
others.
2X
Plus y equals 17. Should we use Cramer's rule just to remind you of it? No? No, you just want to use, what do you want to use? Substitution? Okay, if we're going to substitute, I think it would
I
be,
think elimination.
oh, I think elimination.
Multiply that top
Goodness,
equation
you chose
by.
the wrong restaurant. I'm sorry, you chose the wrong restaurant. You have to choose again. So we're not going to use substitution. What method do y'all want to use?
I think I heard elimination.
Okay. Which variable are we going to eliminate? The x's or the y? If you choose the wrong variable, you get to choose again.
If we
If we eliminate x, we have to multiply by
-2.
-2. If we eliminate y, we multiply by, I think I like multiplying by -1 more than -2. So I'm going to multiply by -1. So
But
we're
all
gonna
jokes aside, you can use any method you want to use. Substitution, Cramer's
as long
rule.
as your calculations are correct, you'll get the same answer at the end.
I
So-
think that what you're doing is the easiest
Absolute easiest.
way to do it. Multiply that top equation by -1. You're not going to have a lot of negatives that you're at. Well, I'm insulting them.
I know.
think why.
So multiplying by -1, the first equation becomes -1x, keep going, equals, the second stays 2x plus y is equal to 17. Add the two together. -1x plus 2x gives me, okay, 1x. The -1y plus y, that's eliminated. And -13 plus 7 is 4. Where am I going to write 4? Am I going to write it on the top line or the bottom line? Here's my answer column. It's X that you found, so it goes on the X row, 4. So that means this basketball player scored 4 2-point shots. How many free throws did this player score? Has to be a total of 13. 13 minus 4 gives 9 free throws. Or you can plug in, you can say, okay, let X be 4. 4 plus Y equals 13. So Y, 13 minus 4. Either you can logic your way through the 9, or you can use your algebra skills to get 9. Either way, the answer's the same. 4 2-point shots, 9 free throws.
4 2-point shots and 9 free throws.
Any questions?
So, what should y'all be doing during the? Oh, okay.